Hello and welcome to this module on statistical decision theory. So, the goal here is try to give you a framework that we will keep using for the rest of the course, right, for at least for the majority of the rest of the course, and to introduce you to some of the basic notations, and also to talk about some kind of a unifying idea behind what we will look at in different classification algorithms and regression algorithms. Right. To set the tone, let us consider inputs which we will denote by x as being drawn from some p dimensional space, right. So, which we will call RP. Right. So, if you think about what we did in the previous modules, we talked about input that had age and income as the attributes. So, that would mean that P was 2 dimensions, right. So, one of the dimensions represented age, the other dimension represented income. So, what we are doing here now is trying to move to a more general setting where I am talking about any kind of a p dimensional space, right, but P could be much larger than 2. And the output that we are going to be looking at least in the initial regression case that we will see, I will assume that the output is drawn from the real numbers again. So, this would be like the temperature that we saw in the second example in the previous modules, right. So, the input x is drawn from a p dimensional real space, and the output y is drawn from again a real from the real numbers, and in the case of regression, right. So, in the case of classification we will see it a little bit later, the output will come from a discrete space, right. And we will also make an assumption that the data comes to you from some kind of a joint probability distribution, right. So, you do not know this joint distribution a priori, right. So, nobody tells you what is the distribution from which the data is coming, but the assumption that we are going to make is that there is an underlying data distribution, right, like a joint distribution over the inputs and the outputs, right, and that it is fixed, right, and you are going to be given samples, right, drawn from right, you are going to given a set of samples that is drawn from this probability distribution over x y. So, this will be your training data, right, which you will use for both training and possibly for validation if required, right. So, so you are going to get an x1 with a corresponding y1, x2 with a corresponding y2, and so on and so forth. So, the goal is, given such a set of training data, so learn a function f of x that goes from the p dimensional space to the real line, right, where so the p dimensional space essentially corresponds to a point in the input space, and the real line corresponds to the output space. So, the function f is going to take any input that is given to it and produce a number, right. So, the f could take different forms, right. So, we looked at f being a straight line, right, in the example that we saw earlier. So, in such cases, right, so my one example of f would be saying that I am going to predict y hat, right, is equal to f of x, right. Given an x, I am going to predict a label y hat, right, and that is going to be given by some right. Right, so, it is going to be given by beta naught plus beta 1 x1, beta 2 x2 all the way up to beta p xp. So, the one thing which I want you to note here is that this x1, x2, so on and so forth are essentially the coordinates of x. So, when I say x here, x essentially comprises of right. So, this could be age, this could be income, and so on and so forth. So, each one of these corresponds to a different attribute that describes the data, right. So, I can look at this and then I can write f of x as essentially compactly I can write it as right. As an alternate way of writing this is to declare that set right. So, I will set x naught equal to 1 and then I can just remove this special treatment of beta naught and I can just write the summation j equal to 0 to p x j beta j, right. So, is that clear? Right. So, this is essentially what we would do when you are doing linear regression, right. So, another example of doing this is a very popular another classifier which we will call the nearest neighbor classifier. So, where my y hat of x is given by 1 by some number k summing over all xi that belong to some neighborhood of x, right, and sum up all the yi's corresponding to that xi. So, let us assume that my training data looks something like this, right. So, there is a x here, there is an x here, there is an x here, there is an x here, and there is an x here and an x here, right. And let us say that my k is 3, right. So, if I get a query point say somewhere here, I get a query. So, this is my x. So, this is my x1, x2, x3, x4. So, these are my training data, the x1 to x6 are my training data and x is the point for which I want to predict the output, right. So, these are the places which I have already measured it, this is a new point and I want to produce the output here. So, in this case what do I do is I pick the 3 nearest neighbors because k is 3, I pick the 3 points that are closest to this data point, right, find the corresponding y's. So, in this case I will pick y2, y3 and y4 and I will take the average of these 3 points and I will report the value of the function at x is the average of this 3 point, right. So, this is called the k nearest neighbor regressor, right. So, I will just take the average of the outputs of y2, y3 and y4 and report that as a value at x, right. So, depending on where x is I will be picking different 3 neighbors and reporting their values, okay. This is the k nearest neighbor. So, there are different ways in which you can define this function f, right. But remember that we had this discussion in the last set of modules that unless you make an assumption about the form of f, you really cannot do any generalization. We needed to talk about lines in the previous class, but now we are talking about different assumptions for the function f, need not necessarily be lines, okay. In this case it is a straight line, right, but in this case it is a averager, it is a local averager and that gives me the function that I want to learn, okay. So, how do you choose this function, right. So, there could be many different ways in which you can define the betas, right. So, given that I have chosen that this is the way to model the function, how do I pick the betas, right. So, how do I even choose this form for my predictor. So, how do I know that this is a valid form to choose? So, we have to look at some performance measure, so which we will consider in this case is the a loss function, right, which will compare the true output y, right, with the predicted output f of x, right. So, I have the true output y and I have predicted output f of x. So, I will have some loss function that compares f of x with y, and my goal is to find an f of x such that this loss function is minimized. Okay. Right. One of the most popular loss function that people use in the literature is known as the squared error. So, I basically look at right, and the performance measure that I am interested in is the expected prediction error of the function f, right. So, that is equal to the expected value of y minus f of x squared, right. In the case of squared error, so the expected prediction error is the expected value of y minus f of x the whole square, right. So, what is the distribution with respect to which you are taking this expectation, right. So, whenever we talk about the expectation of a random variable, so we will have to talk about the underlying distribution, right. So, what is the distribution with respect to which you are taking this expectation, right, exactly the joint distribution of x and y, right. It is the joint distribution between x and y. So, that is the distribution with respect to which you are taking this expectation. Therefore, I can write this as so, I can do a little bit more sleight of hand here, right, and talk about the conditional distribution, right. So, if you remember, the probability of x comma y can be written as probability of y given x into probability of x. So, it can be written as probability of y given x into probability of x. This is just the product rule in probability. So, I get this. So, what does this tell me? That okay, there is some chance with which I can choose a data point x, right. Having chosen a data point x, okay, so what is the probability of seeing a particular output value, right. So, why are we looking at probabilities here again? So, this helps us to kind of model a variety of different scenarios. So, the first one is if there is noise in the measurement, So, I am talking about what is the probability of y given x. Suppose I am telling you that I am measuring the temperature at 3 o'clock every day, right. So, there will be some kind of a natural variation in the temperatures measured at 3 in the morning, right. So, that is modeled by this probability, right. There will be some set of temperatures that are very probable and some set of temperatures that are not, right. So, for example, if I am measuring temperature at 3 a.m., right, so 40 degrees is not a probable value, right. So, those will have lower probabilities, and then say something in the 20s will have a higher probability, right. So, I am talking about Chennai. If people are wondering how you are getting 20 degrees early in the morning, right. The second factor that this allows us to look at is our ignorance about the whole system, So, I might have just chosen the time of day, maybe there are other factors I should have taken into consideration while I am forming my data. So, these factors about which I do not know anything will appear as noise, So, it is not important whether I take the temperature at 3 a.m., maybe it is important where in the building I do the measurements. Maybe I am measuring it next to the kitchen where things will be warmer, or maybe I am measuring it next to an air conditioner where things would be actually warmer if I am measuring it on the external of the building, right. And or I could be measuring it on the inside of an air conditioned room, the temperatures could be lower. So, even though I say I measure it at 3 am, there could be many such factors for natural variations, which I have not modeled. Okay. So, this is beyond the natural variations in the system, right. So, one way of arguing about it could be to say that hey, the natural variations are due to factors that you do not know anything about, right. So, that is a valid argument. So, it could very well be that. So, it is really there is nothing like a natural variation, there is no real noise. So, everything arises, all the uncertainty in the data arises from my lack of knowledge, but that is a philosophical question. So, there is things that are measurable which we do not measure, right, and that I would call as lack of knowledge, and things which are unmeasurable which I would call as noise, right. There could be both of these sources which introduce the probability into our system, right. So, it is not just a mathematical whimsy that we model this as a joint distribution, but there is an actual practical reason for talking about probability distributions here, right. So, now I can go back and write my expected prediction error as an expectation over x of so, an expectation over x of the expectation over y given x, because I have written these probabilities out like this. So, I can write the expectations out also like this of this quantity, right. It is the same quantity earlier, the only difference is now I am conditioning it on the value of x, right. So, what this expression says is, okay, I will tell you what x is, okay, I will tell you what x is, then you tell me what the error will be, right. So, the uncertainty here is over the value of y, right. So, I will give you x, I will fix x, you tell me what y is. So, I am going to look at the error just on conditioning, after conditioning on x. So, this will only look at the variation on y, and the outer expectation gives me the variation on x, right. The outer expectation takes care of the variation on x, right. So, now I can try to find the minimum of this prediction error, right. I can try to find the minimum of this prediction error by conditioning on a specific value for x, right. So, I will not look at this expectation, right. So, I am not making any assumptions about f, right. I am just assuming that f can be anything, right, any function in the world, right, f can be any function in the world. So, what I want to do now is I want to look at each and every value of x, and I want to say that I will pick an f such that for every value of x, right, it makes the best possible prediction, right. I will pick an f such that for every value of x it will make the best possible prediction, right. So, what does that mean? So, it will produce a prediction. So, f of x for a specific value of x, f of x will give the output such that this inner expectation is minimized, right. So, I am going to write it down like this. So, for a specific value of x, right, this is f of x for a specific x. So far I was writing capital X, which is the random variable, right, but here I am using a specific x. Right. So, given an x, right, f of x has to be a specific number, right. So, let us say somebody with an age of 25 and income of 15,000 rupees walks into my shop, I can only give one output, right. He is going to buy a computer or does not buy a computer, or I am going to say I am measuring the temperature at 3 am, what will be the value, right. I can give you only one number since I have already fixed the input description. So, I am going to give you one output corresponding to that input description. So, that output let me call as C, right. So, that is C. C is the output that I am going to give for f of x, right. C is the output I am going to give for f of x. So, what is the value that I should choose for C? Okay. So, it should be such that the error, which is y minus c squared, is as small as possible, right. So, I am minimizing over the different possible values of C that I could assign for f of x. I am trying to pick that C which gives me the smallest error, right. So, arg min means first minimize with respect to C and take that argument, basically take that value of C which achieve this minima. Right. If there are multiple values that gives you the minima, you can pick any one, right. So, this is essentially called conditioning on a point. Right. So, instead of conditioning on the random variable x, right. So, I have conditioned on a specific point where x equal to small x, right, and then I can find this. So, now what happens, for every possible input x that I could have, small x that I could have, I will find the corresponding C and I will say f of x equal to that C, right. So, the thing to note here is I have not made any functional assumptions about what this what should f look like, right. So, f could be something really jagged, I do not care, right. So, this is a recipe for disaster as we saw earlier, right. You might end up overfitting the data, but just work with me here because we are just trying to build some general principles, right. So, we can go a little further, right. Now that we have decided to say that the minimizer is the one that the value that you assign to f of x. So, what is the value of C that will minimize this expression? Right. So, I have to look at y minus c squared. So, I have to assign a single value for C. So, let us imagine what does it mean, right. Suppose I give the input as x, I make a measurement, let us call it say y1, right. I give the same input x again, I make another measurement, say y2. I give the same input x again, I make another measurement y3. So, I have 3 measurements y1, y2, y3 for the same input x, right. Now, I am asking you to give me a prediction for what will be the output given x, right. So, what should your prediction be? It will be the average of these 3 y's, right. So, y1 plus y2 plus y3 divided by 3. So, that should be the prediction. So, why is that the case? Because if you are talking about squared error, right, the quantity that will minimize the squared error is essentially the average, right. So, I will end up writing that f of x equal to the expected value of y given x equal to x, right. So, this is essentially what my prediction would be. So, this is the known as the conditional expectation, right, or so sometimes called the regression function, called the conditional expectation or the regression function. Okay. So, there are a few problems with this, right. So, what are the problems? A, I do not know this distribution, right. So, I do not know the distribution with respect to which I am taking the expectation. So, what is the distribution with respect to which I am taking the expectation? That is essentially probability of y given x, right. So, that is the distribution with respect to which this expectation is being taken, and I do not know that. If I know that, my life is a lot simpler, right. So, I actually have to estimate it from the data. So, what is the data that is given to me? I have this pairs of x1 y1 to xn yn. So, that is the data that has been given to me, and I have to do this estimate of this expectation from that data, right. So, how will you do that? So, it is very simple. You know that you can always estimate the expectation by taking averages. So, what you would do is from your data you pick all the training data points that have this value of x, right. Find the corresponding y, take an average and you are done, right. So, one simple way of thinking about it is to say that okay, I can't find the true f. So, I am going to find an estimate of that, which we will call as f hat. So, is equal to the average of all the yi's such that xi equal to x, right. That is a problem here. Why? So, how many samples do you think you are going to get of the same input x, right, first. The second thing is you are not going to be able to make a prediction for any data point which is not there in the input, right. So, you are trying to make an estimate of the expectation by using the averages, but if you do not have enough measurements, then your average is going to be bad, right. And second thing is you are making an average at that point, and if that point does not exist in your training data, you are not going to be able to return an estimate for it, right. So, we need to address this somehow, right. So, what we will do here is we will relax the conditioning, right, instead of conditioning on a point, we will condition on a region, right. So, what does it mean? So, I am taking the average here of all those data points for which xi equal to x. Now, that is not going to work, right, because there are too few data points. So, what I am going to do is I am going to take this as the average of all the data points which belong to some region around x, which is essentially the neighborhood that we are talking about, right. So, that circle there would correspond to the neighborhood around x. So, I am going to be conditioning on this region which is given by this neighborhood around x, okay. So, does that make sense, right. So, we are not going to condition on a point, we are conditioning around a region. So, the one assumption that we are making here, implicit assumption that we are making here. So, why are we conditioning around a region? So, that instead of taking an average of one data point, I have at least k data points of which I will be taking the average, right. So, that gives me a better estimate of the expectation, right. That is the reason we are doing this conditioning over a region, but more importantly we are also making an implicit assumption. We needed to make assumptions. If you remember, our inductive bias said that we needed to make assumptions. The assumption that we are making is that the output of the function over this region is going to be a constant, right. We are making the assumption that the output of the function over this region will be a constant, right. So, let us try and do a little example so that becomes a little clearer to people, right. Let me go back to my one dimensional example, so it makes it easier for me to draw things. So, I have right. Let us say I have multiple data points like this, right. So, I have a query point and then the corresponding outputs. Okay. So, these are the y's, right. This is x and that is y. So, these are my xi's and yi's, okay. So, this is the training data I have, and now given a query point, let us say I am given a query point here, right. I want to know what is the output value for this x. So, let us say I pick my 3 nearest neighbors, which should be these 3 data points, right, and then I will try to take the average of this, and this, which will be somewhere here, right. I will say that is my output, right. Make sense? So, like this I am going to make guesses for variety of data points, but one thing which I want to point out here is, so I assume that my data point lies here. So, what if I had assumed that my data point was here? If my query point was here, so what would have been the output? So, my neighbors remain the same, right? My 3 neighbors do not change. These are my 3 nearest neighbors, whether the query was here, right? Whether the query was here or the query was here, my nearest neighbors do not change, right. So, what will be the output for this input point as well? So, I will be taking the average of these 3 points. So, the output will also again be that, right. So, in fact, for some region around here where these 3 are the nearest points, the output will be a constant, right. So, the output will always be a constant. So, this is what I mean by saying that we make the assumption that the output is constant in a region, right. So, this region, so for all those data points for which these 3 are the nearest neighbors, so the output is going to be a constant. So, this is essentially the assumption we are making, that the output is going to be consistent over a region, so that I can write an expectation over the region as my substitute. Okay. So, if you think about it, so what have we come up with here? This is essentially your nearest neighbor classifier, right. So, you take the generic idea of minimizing the expected prediction error, right, and then add certain conditions to it. So, what are the conditions you are adding to it? So, you are, well, you can't do the expectation, so you are going to take averages, and you can't do an average on the training data, and therefore, you are going to do an average over a region, assuming that the output is constant over a region. So, conditioning on the data point wise and then conditioning on a region, relaxing that to conditioning on a region gives us nearest neighbor classifiers. So, in some sense you can argue that one way of minimizing the expected prediction error yields a nearest neighbor classifier. Okay. So, in fact, this is a very powerful classifier, and you can show that as k increases, right. So, the estimate becomes more and more stable, you know. So, for small changes in the input data, the classifier does not change tremendously, right, and so as and as n and k tend to infinity or they become large, right. So, your ratio k by n would go to 0, right. In such a case, your f hat of x will go to right. As k increases, the estimate becomes more stable. In particular, as k and n become large, that is, and my number of data points is very large, and so the number of points I can look in the neighborhood also becomes larger and larger, so such that of course, the data points have to grow at a faster rate than the size of the neighborhood. That is what k by n means. So, in which case I can show that my actual prediction I make using this average actually approaches the true prediction that I am interested in, right. So, there are a few caveats here that I need to point out. So, I am assuming I am saying that n goes to infinity. I mean, that is a pretty blase statement to make, because n rarely goes to infinity, right, in fact never. So, coming up with large data sets is hard, except for very rare cases, right, and therefore, you cannot really have a classifier that gives you the right output, right. And another problem is, as p becomes larger, right, as the dimensionality becomes larger, right, generally the data tends to become sparse, you know. So, if I am looking at k neighbors in like a 1000 dimensional space, the area or the volume covered by these k neighbors would be very large, because they are very sparse space, and it is usually not a good assumption to make that the input is actually a constant over this, I am sorry, the output is a constant over this large area, right. So, one thing is, if P is large, right, then if the dimension of the input is large, if you have like 10,000 dimension vector as your input, then using k nearest neighbors is not really a good idea, right. And alternatively, you should also remember that in some cases having a little bit of a bias is actually not a bad thing, right, and therefore we have to look at an appropriate way of representing the function f. Remember, we did not make any assumptions about the function f, right. So, the function f could change as drastically as we want, and so that means that we are trying to keep the bias as minimal as possible, and so we would like to remove that assumption, right. So, moving on, let us look at the linear regression case, where we actually made a significant assumption about the form of the function f, right. Specifically, we assume that f is going to be linear in the input parameter. So, the f can be written as beta 1 x 1 plus beta 2 x 2 and so on and so forth, right. So, essentially our f of x, we assumed it to be, in vector notation we assume it to be some x transpose beta, right. Assume it to be x transpose beta, and so if you look at it from the training data point of view, so I can think of having a vector notation for this, right. So, I can think of a matrix X, right. So, a matrix X in which each row corresponds to an input x y, x 1, right. So, x will be something like right, x will be a matrix that looks like that, and so my beta would be a vector of the coefficient. So, beta naught to beta p, right, and of course, my x is going to have a right. So, the 0th dimension is going to be 1, right, and then going to have beta. So, I can look at the output as essentially being x beta. So, my overall error is going to be y minus, right. So, that is going to be the and that is going to be the estimate of the expected prediction error based on the training data that has been given to me, and I can minimize this. I can take the derivative, right, and then I can equate it to 0, and I can do some minimization to get the value of beta, and that is essentially going to be right. So, take the differential of this, equate it to 0, simplify for beta, right. So, I am going to get beta hat equal to right. This is primarily because of the square here. So, you are going to get this as your simplified expression. So, this is essentially my my beta hat vector, and so remember that the x that we put in here is essentially a matrix where the columns the rows or the data points, right. The columns are the features. So, this will be the like the age of every customer that comes in, this will be the income of every customer and so on and so forth, and each row is a complete data point, right. So, what we have done here is make the assumption that my function is globally linear, and then I have tried to solve for it to give you the parameters beta hat, right. And in the nearest neighbor case, we made the assumption that my function is locally constant, right. So, we start off with the same formulation. We wanted to minimize the expected prediction error, and we make different assumptions. One assumption leads us to linear regression. The assumption that we made was the data is going to be globally linear, and another assumption that we made where the data is going to be locally constant yielded us k nearest neighbor. Okay.